Howdy. The purpose of this video is to identify symmetry elements in point groups and to show how to illustrate those in a stereographic projection. I should point out ahead of time that these images of the molecules are from a website that's hosted by Otterbein University. The link is down here. So definitely it's a great place to go practice these out yourself. You're able to reorient the molecule in three-dimensional space to look at it down different angles. And you can also ask for help to identify these different symmetry elements. So it's a great place to go practice. They have many examples of point groups. But we're going to be working through just one example today, and that is molecule PF5, so phosphorus fluorine 5, 1, 2, 3, 4, 5. And I've just shown two different images of this molecule. The top image is basically looking down this axis, so it looks down a single fluorine, beneath that is the phosphorus, and beneath that is another fluorine. And the reason I've done that is because we can already clearly see that this is a rotation axis of symmetry. That is, an atom up here gets rotated 120 degrees, or 2 pi over 3 radians, gets rotated again another 120 degrees, and a final 120 degrees, and I'm back to the beginning. And so this is a threefold rotation axis. I can pretty easily see that. I'm going to put that here in the center of my stereographic projection. So it's convention to have the highest fold rotation axis located in the center, which means that we're looking down that rotation axis. So as far as terminology goes, I'm also going to be using the phrase in the plane quite a bit, and that's referring to the equatorial plane of the molecule. So all of these three atoms, 1, 2, 3, are all located in the plane. And that's important because in a stereographic projection, anything that's in the plane is going to show up at the outer edge of this circle. Okay, so I already have this threefold rotation axis. I can see that if I look down any of these bonds, there's a twofold rotation axis. That is, this atom here gets rotated 180 degrees up out of the plane, back into the plane here. And this one gets rotated below, back up here. So there's a twofold rotation axis located along all of these bonds. And so I'm going to show one on the top, which is the same here, because that rotation axis passes all the way through the plane and out the other side. I have one that's located here. And then my final rotation axis is located here. And these should be all evenly spaced from each other. They don't look exactly like that, so I apologize for that. But the twofold rotation axes are each oriented pi over 3 radians apart from each other. So 1 axis, 2 axis, 3 axis. So that's all I see as far as proper rotation axes. Next we can think about mirror planes, and I immediately see that there is a mirror plane in the equatorial plane of the molecule. That is, the bottom atom gets reflected up to the top, the bottom half of this atom gets reflected up to the top half. And so we designate a mirror plane that is in that horizontal plane by a bold line all the way around that outer circle. Sorry, it was bothering me that these were not properly aligned, so I reoriented them so they're all pretty equally spaced now. Okay, so we've identified the horizontal mirror plane. We also see some vertical mirror planes. One example would be something like this, and on the top molecule that passes vertically. So it passes through this threefold rotation axis as well as that twofold rotation axis. And on my stereographic projection, that's going to be a vertical line like this. And I call this a vertical mirror plane because it's the rotation axis that is vertical, that is this threefold rotation axis, is lying in the plane of that mirror plane. The horizontal mirror plane, remember, that threefold rotation axis is perpendicular to it. Okay, so I've located a number of proper rotation axes. I've located mirror planes. I can pretty easily convince myself that this molecule is not centrosymmetric. That is, it does not have an inversion point. This atom here, if I inverted it through the center, I would come out here and there's no atom there. So that means there is no inversion point symmetry in this point group. And that's the same as saying that the molecule is not centrosymmetric. So that's pretty good, but there's one tricky thing left that I haven't really considered yet, and that is improper rotation axes. And so sometimes these are called Roto Reflection or Roto Inversion. You can think about it as a rotation that's combined with a reflection or combined with an inversion. So don't be confused. Just because there's not an inversion point does not mean I cannot have roto inversion, because roto inversion is a compound symmetry operation where I do both of those things simultaneously. I rotate and I invert through. So this particular point group has examples of improper rotation axes in it. And the operation that we're looking at is either called a threefold roto reflection, or that's equivalent to a sixfold roto inversion. So it kind of seems weird that these two things can be identical, but let's think about what that means. And I can illustrate it here off on this molecule over here. So let's say I start at some point, and we're going to think about what does a threefold roto reflection mean. That means I rotate 120 degrees and then reflect around a perpendicular plane. So a general point that starts somewhere here would be rotated 120 degrees, and it would end up below the plane. So I started off above and I end up below, and it's been reflected. So I'm going to put a little comma there. And I do that again. I rotate 120 degrees and now it gets reflected above, and there's no comma there. 120 degrees, I'm back here, but now I'm getting reflected below. And so there is a comma on that left-hand side. 120 degrees, now I'm above, but no comma. 120 degrees, now I'm below, and I've been reflected, so there's a comma. And then if I do it again, I'm back to the same point. So the net effect of a threefold roto reflection operation is that I end up with this general position, which is both above and below, and one of those is reflected, has changed the handedness of the sign. So that's a threefold roto reflection. A sixfold roto inversion means, I'm going to choose a different color for this. Let's say I start out, I'm just going to put this one just next to it because that'll be easy for us to see. And I'm going to start out above the plane. Now, a sixfold rotation is going to bring me pi over 3 radians over here, and then I invert through the center point. And so that's actually going to put me below the plane, and because I've inverted, I have a comma. Now I do this operation again, and so I rotate pi over 3 radians. I invert through the axis. That's going to bring me here. I was below the plane, so now I'm above the plane, and no comma. I have not reflected. I do this again, pi over 3 radians. That brings me here, and I invert through, and so now I'm below the plane with a comma. I do it again. I invert through. I'm above the plane, no comma. And one more time, I come down below the plane and a comma. And so you can see that these orange general points are exactly identical to the aqua blue inversion points. The only reason they're not at the same position is because I offset it a little bit just so we wouldn't be on top of each other. But this is an example that shows that the threefold roto reflection operation is the same as the sixfold roto inversion. And so you can work through this operation to convince yourself that that's true. Now it turns out that if I have a threefold rotation axis and it's perpendicular to a mirror plane, that means I necessarily have to have this improper rotation axis as well. That is, threefold axis that's perpendicular to the mirror plane means that I also have a coincident improper rotation axis. And I could either designate it threefold roto reflection or a sixfold roto inversion. The same does not operate the other way. That is, if I have this, that does not necessarily mean I have threefold perpendicular to mirror, but it operates in the one direction. And so the symbol for a sixfold roto inversion is basically a triangle inside of a hexagon. And it kind of looks to me like a triangle that's a threefold rotation that's perpendicular to some kind of plane. And so really that's giving you a hint that this sixfold roto inversion is the same, or it definitely occurs if I have a threefold that's perpendicular to that mirror plane. Okay, yeah, so that is it. That is all of the symmetry operations that I have present in this point group. I can now give it a name, and if I use the Schoenflies notation, it's called a D3H point group. If I'm using the notation of the that's used in international crystallographic tables as Hermann-Magin notation, it is referred to as 6 bar M2, and that's the sixfold roto inversion axis perpendicular to a mirror plane and perpendicular to twofold rotations. Okay, and I do need to back up and correct one thing that I said that was incorrect. This equivalence actually does go both ways. So if I have a threefold rotation axis that's perpendicular to a mirror plane that is identical, that means that I do have to have a threefold roto reflection or a sixfold roto inversion axis there. So these two are exactly the same thing.